In this video, I'm going to use the first derivative test to find what the local extrema are for this function f of x equals negative x cubed minus 3x squared plus 2x minus 3. So the first thing we do is we take the first derivative, f prime of x equals negative 3x squared minus 6x plus 2. We set it equal to 0. We're going to create a sign chart, right? 0 equals negative 3x squared minus 6x plus 2. Use the quadratic formula, negative b, so that's 6, plus or minus the square root of b squared minus 4ac, that's 36. It's going to be plus 6 times 4 is 24, over 2a, which is negative 6. So that's negative 1 plus or minus 60, so square root of 15 over 3. So these are the critical numbers. We're going to draw our sign chart for the first derivative. So we have two critical numbers, negative 1 minus square root of 15 over 3, and negative 1 plus square root of 15 over 3. We put in a very large negative number to look at this region. First term dominates, so it's a negative 3x squared, so the function is negative. Put in a very large positive number. First term dominates, it's negative, so again, the first derivative is negative. Again, in this region, negative 1 is a nice number to put in, so we have negative 3 plus 8 plus 2, so it's going to be positive. So our function is decreasing, increasing, and then decreasing. Our critical numbers are negative 1 minus square root of 15 over 3 and negative 1 plus square root of 15 over 3. These two numbers are where we potentially have local extrema. We think about this first one, and we say to ourselves, well, it's decreasing, then it's increasing. So the function's decreasing, then it's increasing. That must be a local min at f of negative 1 minus square root of 15 over 3. I'm not sure I want to calculate that. And then here, the function is increasing and then decreasing, which means we have a local maximum at f of negative 1 plus square root of 15 over 3. And again, I'm not sure I want to do that calculation, but basically I could plug these numbers into this function and I would find out at what values we have a local minimum and a local maximum.